Folks, just a few words of welcome from me, and to many of you I'm sure it's welcome again, so I won't say anything about the Newton Institute. You know lots about it. Firstly, just to say thank you all very much for coming. It's a great turnout, and I hope that you have an interesting time, and we're certainly going to be discussing interesting things. I'm particularly grateful to Caroline for taking over as the founding chair of the network of correspondents in the UK. Those of you who were here last time will recall that we had a helpful discussion about the role of the National Advisory Board and the role of correspondents, and that evolved actually to the National Advisory Board standing down on the assumption that the role of the network of correspondents would actually be beefed up. And I think that's been happening, and this meeting is a sort of part of the start of that. One of the most significant things has been obviously the appointment of an independent chair. That was from nominations received from Novella Societies, and I'm really delighted that Caroline has taken that on. And it has transformed the feel of this meeting, in fact, because now there is one of you, as it were, in charge of it, and that's exactly the way that it should be. So that reflects a really significant change in the governance of the Institute. And Caroline is also on the management committee of the Institute, so that's more of the national community there. And we've changed from having a Cambridge, part of that governance change has been moving from an internal Cambridge person as the chair of the management committee through to having an independent external person, in fact someone with a maths background who's been in the city. So all of these are great changes which flowed from last year. The structure of this meeting as well is a significant development, and I'm really grateful to Ben and to Caroline for developing that. And we've got two significant things to talk about: the 10-year vision and the gender balance. And as far as the 10-year vision, I'll be saying a few words of introduction about that, and Ben will introduce about the gender balance, but then we'll be into the discussion groups, which is why I had a double take when I came in, but of course the room is set out like this so that it can facilitate the discussion groups. I think that's probably all that I want to say by way of introduction, except thank you all very much for coming. Maybe the formalities, I should say: switch off your mobile phones. I guess everybody knows that the talk, and I suspect the proceedings, are actually going to be recorded. So switch off your mobile phones, otherwise they will be picked up. Should I say anything more, Ben, or is that enough by way of formalities? I think without that, without any more ado, can I just hand over to Caroline, and Caroline's going to chair the rest of the day. And Caroline, really say again, really grateful to you. Thanks very much.
Well, thank you. So I don't want to take any more time now. So I don't think any of us quite know how this is going to work out, having chair and correspondence, but I hope that we will manage to prove ourselves to be a really effective voice for the whole UK mathematics community to somehow get the thoughts and ideas and suggestions and so on of people who are really out there, back directly, more directly than previously, to the Newton Institute. So I'm here to facilitate that. So I'll talk a bit more about that later on, but the first item today is mathematics, as it should be. So I'm very pleased to introduce Professor Iain Gordon from Edinburgh, who's part of one of the two programs currently going on, the Algebraic Lie theory program. He's going to talk here about algebraic Lie theory through the symmetric group. So thank you very much.
Before I begin, I should like to thank the organisers of the Algebraic Lie theory programme. I should like to thank them for giving me the chance to talk here. Not only is it great to be down in Cambridge in its 800th year and at the Newton Institute, it's also, I saw this morning, great to be here because Scotland has reached pandemic level 6 with swine flu. Most of it is based in Glasgow, I think, not in Edinburgh, so I'm not so happy to see Chris Aythorne here, who is the Glasgow correspondent. But anyway, thank you very much. So, I want to try to illustrate some of the themes that are in algebraic Lie theory just by doing one example, which at first sight, it might look only superficially that it's close to algebraic Lie theory, the symmetric group, but somehow it's really at its heart, and some of the techniques that are used in the symmetric group, in the representation theory of the symmetric group, are really fundamental techniques from algebraic Lie theory that illustrate quite well, I think, some of the things that people here are thinking about. So before I even begin, I just want to make sure that we're all going to agree with what the symmetric group that I'm going to be looking at is here. So I'm just going to fix a set, finite set 1 to n, and then the symmetric group is just going to be the group of mappings that are bijective. So just permutations of 1 up to n, and it's a group under composition of these mappings. And then if you were to stay at this from this point of view, if you don't believe that the symmetric group is important to look at just because of this sort of fundamental definition, there are other reasons why in finite group theory you would just be forced to want to understand the symmetric group and everything that you could about it. The first one is Cayley's theorem that we teach to our undergraduates. If you start with any finite group, you can embed it inside the symmetric group, asymmetric group, for a large enough number of integers. In fact, you just take the order of the group. That will do. So that tells you, of course, that the structure of the symmetric group is very complicated. It includes in it all of somehow finite group theory. Another reason is this is very close. It has this normal subgroup, the alternating group on n letters, so the group of even permutations, and that's a simple group. And that's, of course, one of the building blocks of finite group theory. So the symmetric group, I claim, is a sort of fundamental object that we should try to understand in as many different ways as we can. Thank you. Yes, you're right. For n large enough, yeah. So now, algebraic Lie theory. So when I got down to writing this, I suddenly realized I didn't know what algebraic Lie theory meant. So I went to the companion to mathematics and I found Lie theory, which was a wonderful article, but it didn't really explain the adjective algebraic in front. The only consolation I had was the thing that comes directly after Lie theory is linear and nonlinear waves, which is the topic of the talk later this afternoon. And I know that it's even harder to try to define an integrable system than it is to try to define algebraic Lie theory. So here goes. I'm going to take this as you can say many nice things about algebra and many unpleasant things about algebra. I'm going to take this sort of banal definition of what I would like to say algebra is going to do. So it's essentially structural from what we're going to do here. On the other hand, Lie theory was built up to study continuous or smooth sets of symmetries. And when we want to try to combine these two things, that tells us that we want to try to look at groups that have some nice topological continuous structure, but that structure should be algebraic appropriately. And a perfect example to illustrate this is if you start with n by n matrices over some field, you can take the complex numbers or the real numbers if you like, then I could think of this, if I wanted to think of n by n matrices, then one thing I could do would be to look at functions on this. These functions form a nice commutative ring. They're polynomial functions in n squared variables. And then the determinant is also written out as a polynomial. And so if I want to have non-zero determinant, I'm just putting on some polynomial condition on this space. And so this space is somehow sitting naturally inside a space of dimension n squared. So it's an algebraic group. It has some structure of an algebraic variety. And at the same time, it's a group. And the group multiplication and inverse are compatible with this sort of structure. So then I think probably it's fair to say that most people here at the program will be studying not just all types of groups that appear in this way, but maybe linear algebraic groups. So I just want to say that these would be sort of nice subgroups that we would get from the general linear group, like so. And then if you're thinking algebraically and you want to try to classify such things, well, immediately you come into a dichotomy that's sort of a classification splits up into two parts. The sort of ironically solvable groups are the difficult ones, and you get simple groups appearing. And it's one of the beautiful parts of the theory from the early 20th century, really. When you try to classify these simple groups, they have a very, very beautiful combinatorial classification in terms of things called Dinkin diagrams. And so you start to see a host of combinatorics appearing. These Dinkin diagrams fall into families. There are 4 infinite families, and there are 5 exceptions. The exceptions are called E, F, and G. And what you immediately realize from that is that classification itself is extremely beautiful. It also means, in some sense, you can really get your hands on these types of groups. They're things that you can calculate with, and so on. And associated to them as well are the infinitesimal counterparts, the Lie algebras, and they're also central to this field. So maybe it's better to, rather than try to define anything, to give a flavor of what problems in algebraic Lie theory might be. So they typically will feature these groups, usually these simple groups to begin with, but then also automatically things like these solvable groups start to appear. It involves combinatorics essentially because the classification involves combinatorics, but it's seen very often as a dirty trick if you try to use too much of the classification. You should do things in the right level of generality. So something, if it's some facts are true in general, and you should find the correct proof of this rather than going to the case-by-case analysis that you can do, and then fiddling around with the combinatorics there. And the final part, the flavor, is that these groups are so natural, things like general linear groups, that they appear in many, many different types of mathematics, anywhere where you have some kind of symmetry. And particularly the tools that are used here come from algebraic geometry and algebraic topology, and there are very strong interactions as well with mathematical physics. Okay, so it would be reasonable to ask, I think, at this point, what does a symmetric group, which is just a finite group, how does such a thing appear in this algebraic Lie theory where really we're trying to study continuous groups? Well, it appears as follows. I mean, one of the ways that combinatorics appears, it appears by, you have these groups are typically infinite, but you may have, it may be acting on certain sets, so these groups are symmetries of things, and you might have large commuting actions of operators. And so the typical example would be inside the general linear group there is this diagonal subset, and these elements commute with each other. So we have this algebraic torus that sits inside here. It's commutative. And so the combinatorics appears essentially by trying to understand, if you have the whole group acting on something, try to understand how perhaps that torus will act. If they're acting by commuting operators, you can try to simultaneously diagonalize actions and things like that. And so a typical example of this is when you want to try to classify things like, there is something which we'll come to later called finite dimensional representations of these groups. Well, you may have geometric spaces that this general linear group here acts on. The torus will therefore act on it as well, and often, if the space originally that you were working with was compact, often a lot of the structure will be controlled by the action of the torus, and in fact by the fixed points of the torus. And a very famous example of this is a classical theorem in the representation theory of these called the Weil character formula, which allows you to move from problems about the whole group to things to do with about combinatorics of this torus and functions on it. And then when you're starting to look to see how this torus might act, you could then say, well, we've still got the larger group here, this general linear group. I'm going to go to this here. We have this general linear group, and some of the elements of the whole group will preserve the torus. If I multiply the torus on the left or on the right, I'll get the same answer. So we get this normalizer. The normalizer will preserve the set under conjugation it contains the torus, because of course the torus commutes with itself, and so therefore you find that on things attached to this torus, you very often have actions. If things were arising already from the general linear group, you have the normalizer factored out by the torus doing something, and that's the symmetric group. As you can see in this example here, a typical type of thing you might have is permuting these entries around here, and so you have permutation matrices living inside the general linear group, and they provide a good set of coset representatives for this. And so it's completely natural that if you want to try to understand the general linear group and try to use this process of moving things to combinatorics, you get automatically into the world of the symmetric group. And that gives you an indication of one way in which the symmetric group will appear. Its correct generality, the symmetric group is attached to the general linear group. The general linear group is essentially one of the family that I talked about when you classify simple groups. So you have everything else, all the other similar types of groups that appear in the classification, and these are called Weil groups, which are examples of Coxeter groups. And that's often a correct generality in which you want to try to study the symmetric group. That's a very special type of a group with a presentation. Okay, so that's why they appear. So that's a way in which the symmetric group appears and helps you to try to understand the representations of the general linear group. But rather we want to go the other way. We want to switch back to the original problem of understanding the symmetric group, and we're going to try to use in a much more non-obvious fashion how to get hold of, how to find algebraic Lie theory appearing in that. So I just want to make one point before trying to justify from a group theory point of view why you would like to study representation theory. So it's kind of obvious that group theory has a numerological side. So the first three theorems are theorems that we teach to undergraduates. The last one isn't. And so the first, they're telling you about numerical properties like the order of the group or the order of subgroups and so on. They have certain numerical properties, and these numerical properties are constrained. And exactly how these are, they produce structure inside the group. And so what you would like to do is find much more sophisticated numerological information as well, and representation theory allows you to do this, particularly via character theory. So one of the things that representation theory will produce for you, it produces lots of numerological information, and this numerological information then has very strong consequences for group theory. On the other hand, this is not why I would study group representation theory. I study it, I think, because simply groups are supposed to be symmetries. Symmetries of what? And representation theory is trying to tell you exactly what they act on. So I just want to remind you, perhaps, of the definition of a representation. For what we're going to worry about are groups G here. We're going to be thinking later of the symmetric group, so it's going to be a finite group. We'll have a finite dimensional vector space over some field and a homomorphism of groups. From that group into the general linear group on V, that's just the set of invertible linear transformations of V. And so the right way to think about it is that group theory is somehow inherently, from its axioms, nonlinear. And what you're doing is trying to linearize this, perhaps, by saying that each element of the group is acting as a linear transformation on some vector space. And so often when you start off, for instance, this is a very common thing that you would already do in geometry. You have a group acting on some geometric space, and so you try to linearize it by looking at tangent bundles or looking at vector bundles more generally on this space, and they often inherit actions of this group there, and the group is now acting linearly because those objects were linear. And so we would like to try to understand what these things look like. So I want to give you 3 examples to begin with. So the first example is one that apparently carries no information at all. I just take a one-dimensional space and I send every single element to the identity mapping. So in other words, I say every element of G does nothing at all to this vector space, just the identity. Another example which comes specifically from the symmetric group is I could still start with a one-dimensional space, but instead of doing nothing for the elements, I know that the elements fall into 2 sets, the ones that have got even permutations, the ones that are odd permutations, and I can ask even permutations do nothing, odd permutations multiply by -1. And then another example, the symmetric group acts obviously on sets of n things, just permuting these n things around. And I just want to point out one thing here, if you were to think about it for a moment. The first example comes from, if I took the symmetric group in the first example, it comes from acting trivially on a set with one element, essentially. The last example comes from acting on a set with n elements. And if you think about it for a moment, you'll see that this example in the middle doesn't come from a permutation, typically, for most fields. Here, it doesn't come from the group acting by permutations on something, it comes from something else. And so it's a little bit of linear algebra thing here. And so I want to do a calculation. This set at the bottom, where the symmetric group is just permuting coordinates on n-dimensional space, splits up into two pieces. So one piece is where I make all of the coordinates the same. I can see if I move these around, nothing ever happens, so that looks like a copy of the trivial representation. And on the other hand, if I take the set of n coordinates where they sum to 0, then as I move these around, this sum to 0 will never change again. So that's another subspace inside. That's a linear condition, so that's another subspace inside there. And so we've produced the whole representation splitting up into two pieces. You see, because if you try to check that these things are actually giving you distinct subspaces, then you find it's going to be absolutely fine unless, well, the problem might be that this element here, an x, 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 can sometimes sit in this set. So that would be adding together n copies of your of some number here, and that would be in there as if n was equal to 0 in the field. So if you were working in finite fields where the characteristic might be p, so the number p, if you add 1 together p times, you get back to 0, will tell us that in characteristic p, some interesting things can happen which you don't see in characteristic 0. Okay, so that's the first time such a phenomenon appears. So I think that probably most people who are part of the algebraic Lie theory meeting here will think of themselves in some sense also as representation theorists. And so a representation theorist, if they're an algebraist, they like to classify things, and so they try to classify what representations can appear. And representations are exactly as you would try to classify things in chemistry, I suppose. You try to build up, first of all, the atoms. So these are the irreducible representations, like so. So these cannot really be split up into smaller pieces. And then from these irreducible representations, you can then try to glue these together to build up the analog of the molecules. These are the indecomposable representations. And if you fix a finite group, then you'll expect to only have a finite number of irreducible representations, but an infinite number in general of indecomposable representations. And so the first goal that you would have would be to try to describe what these irreducibles are. If you could do that, you might want to know how do you glue them together to produce something more complicated. And then also, that's the sort of internal part of it. If I'm trying to argue that groups appear naturally as symmetries of things, then somebody will come up to you with a representation and they will want to know how to describe it in the things that you understand. And so there's a second problem, which would be if somebody gives you the group acting as symmetries, how do I break it up into things that I already understand? These are sort of two very basic problems of representation theory. And then there's a theorem, an ancient theorem in the field of Mashka that tells you my analogy with chemistry, that this is atoms and this is molecules, is a terrible analogy because there are no molecules. There are only atoms. Okay, so Mashka's theorem tells us that everything will decompose as a direct sum of irreducibles. So to understand the representation theory of a group G, as long as the characteristic of the field doesn't divide the order of G, so you see some numerology coming in here, we only have to describe the irreducibles. But this second question here is still an interesting question, okay, even though we don't have to worry about the complexity of indecomposable representations. Okay, so that's general theory. Let's apply it to the symmetric group. Here would be the question. Describe the irreducible representations for every single n. And I claim that this is a central problem of algebraic Lie theory, even though we've only made somehow a small but very, very central connection between the symmetric group and the general linear group. So I want to try to illustrate that for the rest of the talk. So first of all, There's obviously this problem is infinite because there are infinitely many n. But it's infinite as well because there are infinitely many fields. Okay, so you have to worry about the two parts of infinity. And we've seen if we chose a field with characteristic 0, Maschke's theorem has already told us that the problem becomes easier. We only have to worry about everything will basically split up as a direct sum of these irreducible representations. And in that case, over C, but in fact you could have worked over the rational numbers here, Frobenius described everything. Okay? So you might ask, why do I want to tell you about something that happened over 110 years ago, I suppose? Well, if we work over the fields of positive characteristic 2, 3, however high you want to go, the most simple questions remain unanswered. Okay? So one of the things that's hidden in here is we have to define what described means. Okay? Because we do know some things about this, but we know very little. And one of the ideas that has come out of algebraic Lie theory, I think, in the last 20 years is there is a way to look at this description of the representation theory of the symmetric group that generalizes somewhat to positive characteristic and generalizes very beautifully to some replacement of positive characteristic, which is what I want to try to explain. So a typical question would be, first thing would be, give a list, tell me the number of irreducible representations for a symmetric group. Once you've done that, they're supposed to be vector spaces. The next thing you would ask would be, tell me the dimension. So we know the numbers, but we don't know the dimensions in general. Okay? In positive characteristic. So let's start with characteristic 0, but I want to present it in a way that will require no general machinery and only a little bit swept under the carpet here. So let me just tell you first of all what we expect to go for. So I like this sequence of numbers that goes like this. It's going very well. And then something strange happens. Okay. So this set of numbers here is the sequence of partitions of the numbers 0, 1, 2, and so on. This is a set of numbers that dominates representation theory of the symmetric group. So by a partition, I just mean pick a number, partitions of 3, then it's just going to be the different ways that I can write out 3 as sums of positive integers. Okay, so there are 3 of them there, then 5, then 7, surprisingly, and so on. So this was studied, and the sort of asymptotics of this was studied by Hardy and Ramanujan, and so on. And Frobenius' theorem from a long time ago says that the number of irreducible representations of the symmetric group over the complex numbers is the same as the number of partitions. And this is just a special case, actually, of a general theorem, which is a very important, with an important proof, general theorem as well. Numbers of irreducibles of a group are the same as number of conjugacy classes. And again, one of the elementary things that we teach students in group theory is how to describe conjugacy classes by partitions. So therefore, by this theorem, numbers of representations are the same as number of partitions. The important thing about this is that it does not assert any bijection between these two sets here. These two sets, in some very precise sense, are dual to each other. The irreducible representations and the partitions, it's not telling us how to go between these two sets here. So for instance, when we looked at the symmetric group, I gave these examples of the trivial representation, the sign, the permutation representation. Then we've already seen the number of permutations of 3 is 3, but I haven't told you how to associate one of them to one of these representations. So I could do it like this, but I have to justify why I would do it like this. Okay. And an important point about how to justify this is to understand how this would generalize into positive characteristic, where we have an analog of this theorem due to Brouwer, and we want to try to understand in a very precise way, structurally, how we can produce such a bijection. Okay. So a good way to think about it is to have a chain of these symmetric groups. They lie naturally inside each other. Remember, we had the set In of n, the first n positive integers. So if something permutes, if it fixes n, then it permutes the other n minus 1. Then the symmetric group is sitting, the symmetric group on n minus 1 letters is sitting inside the symmetric group on n. Okay. So if we do that, if we had started off with one of our irreducibles, our atoms, for the symmetric group, we could restrict it. So this was just telling us that every permutation acted on this set. So we can restrict it just to the permutations that come from here. They still act on this, so this is still going to be a linear representation. And because of this theorem of Maschke that I told you, we're working over the complex numbers, this has to decompose as a direct sum of some irreducible representations for the symmetric group in n-1 letters. And then there is some relatively elementary linear algebra in this specific case of symmetric groups embedded inside other ones that will tell us this here, this direct sum decomposition into atoms. Each atom appears only once. There's no multiplicity. This is the crucial result of essentially the crucial result of the whole theory here, this multiplicity one result. So each of these VJs that's appearing is different from each other. That's something special about the symmetric group here. So let's just do an example again. This permutation representation was three things under the action of permutation where we assumed that we added them up to be 0. I can split that up when I restrict only to allowing permutations of the first two parts, so permuting 1 and 2, it splits up, and I've written it out precisely how it splits up there. If I take a typical element, I can write it out like this. Notice if I add this entry with this entry, I do get 0 because of this condition here. And so therefore, if I'm only swapping the first two entries, nothing changes here, whereas these ones added up to 0, so if I swap those two, I multiply by -1. And so it splits up into something that's trivial and something where I'm acting by -1, so I get that. So we encode this in a graph. Exactly what happens here. The graph has vertices that will be these irreducible representations, and we don't know, that should say the symmetric group on n, sorry. We don't know what those are yet. We're going to pretend we don't know what those are yet. And the edges of this graph should be what happens when I restrict from one symmetric group down one level. So for instance, we could start off with the representations that we already know about up to S3. We've just checked that if we start with the permutation one, it splits up into the direct sum of these two, so there's an edge between these. And if we do the whole thing, this is small enough, you just do it by hand, you get this picture here. And of course, this is supposed to carry on forever downwards as the symmetric group gets larger and larger. So let's just think what this is going to do for us. So obviously, just by definition, this graph is telling us how to restrict one representation to another. But it's doing one other thing as well. If you think about repeatedly doing this restriction, so I start at this one, then I restrict, then I restrict, then I restrict, I'll be moving up this graph very slowly, and I'll be following a path in this graph. And the multiplicity one result that we had says that by the time you get to here, where you've basically got no symmetric group acting, you're just thinking of the thing as a vector space, then one of these paths will correspond to one element inside this representation. It's just one way to describe one element. And another path will correspond to a different element. And what's happening is that this representation here, you could describe a basis for it just by restricting, 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 and seeing what the different paths would do here. So the paths inside this graph give us a basis for these representations. So if I just go through that, there were these two paths, and remember that this representation was a three-dimensional thing with one linear relation, so it became two-dimensional. So that tells us that actually what we would like to do, not to think precisely about us being in this representation theoretic situation, but rather to think about trying to describe explicitly what this graph is into something that we already know. So we want to identify that effectively. So remember, the crucial point is we start with a representation and we restrict it. So restricting it tells us to forget about what happens with the whole symmetric group action and only think about what happens if you permute the first n-1 things. Now that would be forgetting some structure that's around, and so we want to remember that structure. And so we can construct an element. This is a sum of operators. These are the transpositions that swap the number m and the number n. They live inside this symmetric group. I can take each of them, gives me an operator on the vector space V. I can sum up what these operators are. And if you look and think about it for a moment, you'll see that such an element will simply commute with any permutation that comes from n-1, because all that will happen is these numbers here, m's, will get permuted around. And so therefore, there's a simple lemma called Schur's lemma that will tell us that this operator will act by scalar multiplication on each of the different things, the summands of this here. So I just do the example again. L3 is just going to be the sum of how the transposition 1, 3 acts and the transposition 2, 3 acts. You work it out, you get this, and you see that you've multiplied by -1. You do it on the other element that you were splitting up perm 3, and you get this. You see that it multiplies by 1. Okay, so that would mean that what we should really do is attach to this graph a 1 here, which was telling us how that operator multiplied there, and a -1, which told us how this operator did. And again, it's simple enough that you can work out exactly what goes on, and you get this picture here. And so you've put extra structure into this graph in order to try to understand what the graph should look like. And so now, associated to each path, we have a list of numbers as well, exactly n numbers if you're at the nth level of this. So for instance, associated to this permutation representation here, we have the numbers -1, 1, and 0. And if we choose a different path, we still get the same list of numbers. That's the general fact here. So then what we can try to do is, if we're trying to label what this thing should be, we could label it with the 3 numbers that we have in this list. So we record these in the following strange way. So you start with the 4th quadrant, and then put a line, the diagonal y equals -x at 0, and then draw parallel lines at 1, -1, and so on. Fill out the whole 4th quadrant. We've only got a little bit of it here. And what you have to imagine is number 0 permeating down one of these lines, the number 1 down this line, the number 2 down this line. And then what we're going to do is, instead of looking at the these different paths, we're just going to record the numbers that we had here. And as we do this, you see the following thing. The sequence that we had attached to this permutation, it was either of these things. So we just put in the numbers, trying to fit them into the top left-hand corner as best we can. So there's the number 0. That's basically the 0, if you imagine it in the middle of that box, is exactly on that line that we started with. We also have to put in the number -1. It's in both of them. It fits in there, and the number 1 fits in there, and that's us told to stop. And if you have a look at this, that's a partition. That's 2 plus 1. Okay. So that allows us, in general, the theory, not in too complicated a way, allows us to attach to any representation, by doing this procedure, a partition. And it's not only a partition, it's a partition where you represent the partition as boxes. And it seems to me whoever did this, first of all, was a genius. Because if you have boxes, you can put things inside them. Okay. So partitions label the irreducibles of symmetric group. That goes back now to the theorem of Frobenius, but we've done it in a very explicit way. We've said to every irreducible representation, we've produced the corresponding partition, whereas before it was just an abstract 2 numbers are the same. Right. So this is a slightly bigger picture of what it starts to look like over here. And so you see, now we have to worry about, we've said that to get here, the paths have the same integers appearing, but we want to keep track of when we added in those integers as well. So if we do that, we can get the following. So at the first step, there was no choice. We have to go here. Then at the second step, we say we go along this path here. We add in a 2 there. That tells us at the second step, it was this box that came in. Oh, I'm going somewhere completely different. I'm not going over there, sorry. The next one, we add in a 3, and then we add in a 4 to get to that one. So putting inside these boxes the numbers 1, 2, 3, and 4, not only it's encoding the partition, obviously, by the shape, but the numbers are encoding the route that we took. There's another route, and you see you get a different set of numbers, 1, 2, 4, 3. That one was 1, 2, 3, 4. And then similarly to go along the last path. And so you see what you can actually do is you can label by these paths. By putting in these paths, that's the same as putting in sequences of rising numbers. They rise in rows and columns. And that tells us, since the paths were telling us the basis, the number of combinatorial data that you can put in like that is going to be the dimension. And this is the abstract definition of what I was doing, taking the boxes for your partition and filling it with numbers. And there exactly are the 3 things that we got for the 4-dimensional representation. And that was a theorem which is slightly newer. Okay? The size of the dimension of a representation is exactly the number of these fillings that you can do. Okay, so it's not news here, but the news is the way that you've constructed this. You've done this without appealing to any general theorems of representation theory, really. Nothing too. It's just a construction that's specific to the symmetric group. So what happens in characteristic P? So remember, we don't know everything, so I can't tell you, but I can tell you something. So Brouwer made an analog of the theorem that we talked about before. To label the representations, you need to have P regular conjugacy classes. This is just conjugacy classes of elements whose order is prime to P. So that means that we want to try to label things by partitions, because that labeled conjugacy classes, but only ones that correspond to special types of elements. Then you have a problem. You have lots of different ways to try to describe these, and which one is the right way? So for instance, over the symmetric group in S2, multiplication by -1 is the same as multiplication by 1 when you're over the field here. And so before we had these two partitions to describe, the first one was the trivial, the second one was the sign. These have now become the same, so which partition should persist? That's the question. And so the idea is simple. We do what we did in characteristic 0 and change it to characteristic P. And modulo horrific technical difficulties, this works. I don't know if you have a look at this. I found this. I'm not sure which way the car is pointing anymore if you have a look at the skid marks. So it's probably just as well that it's black type. Okay, so as we transform, we've got these terrible problems. You can't decompose representations into the atoms anymore. These molecules exist. You've got indecomposables. The integers that were appearing before, these lists of numbers, now have to be counted modulo P, which means that all sorts of things are going to be occurring more than once, whereas they may only have been occurring once in the diagram before. So you have to be slightly more sophisticated. You stick all the representations of the symmetric group together. So we work in a field of characteristic P, that's the F. We put all the irreducibles together, and we add them all up in this Grothendieck group. So this is just a vector space over Q, essentially, where that vector space has a basis, the irreducibles of the symmetric group, the things that we don't know about. Okay? And then, this was the picture we had before. If we look at this modulo P, say P is 3, so I've just put in what you get, then you start to get all sorts of things being repeated, and so on, and it becomes quickly apparent that this is not quite the right diagram to look at. But you still have persisting the fact that you could restrict representations, that's this E, or you could induce representations, and then you could just ask what was the value of that operator on the representation. And this is the miracle that brings algebraic Lie theory back in, that says algebraic Lie theory controls everything about the symmetric group representation theory. These operators, EI and FI, satisfy the relations of the Lie algebra, and it's a very famous Lie algebra. It's affine SLP. So this is a Lie algebra that appears completely naturally in generalizations. It's an infinite dimensional Lie algebra in generalizations of studying simple Lie algebras, and it's very, very natural in the theory, the representation theory of Lie algebras associated to mathematical physics. And it turns out this representation, so these relations that are coming by inducing and restriction, they satisfy the relations of a Lie algebra, and they act then on this space of representations of the symmetric groups via a well-known representation called the fundamental representation. So at that point now, you have this object here, this WP, something that you don't understand very well, but you have extra structure now. You have a Lie algebra acting on it, and the one thing that you have is that you have the basis of this that you want to understand, the irreducible representations. You want to understand the basis, and you know nothing about them yet. So, can that help? And now we get into some modern mathematics. Here's a theorem. I'm very unsure about the correct attribution for this theorem, so I've managed to mention as many people who I thought might be in the audience as I could. So there is one of the organizers. So there is a basis, or some type of basis, for this representation that corresponds precisely to the irreducible representations of the symmetric groups in characteristic P. And these operators that we've just looked at correspond to certain natural things inside this basis that appears from Lie theory called Kashiwara operators. So a crystal basis is you take a representation of a Lie algebra, and it's some basis that was constructed maybe 20 years ago, maybe less, for the first time, that is a simplified basis for representations. It requires some leading order information, and it arises from statistical mechanics originally, and also from geometry. And it's an incredibly powerful combinatorial tool in Lie algebra representation theory. So remember, in particular, for studying tensor products, if you remember the goals of representation theory, this second one, how to decompose things, it's been well known for a long time that we didn't have such a good theory for decomposing tensor products. Crystal bases somehow solved that. So the basis that we get, this crystal basis, corresponds, and the operators that we get, which are corresponding to the operators for the Lie algebra, in this simplified form, they're called Kashiwara operators, produce some graph. And it turns out that that graph is essentially the branching graph that we talked about before. So this is what happens if I do from characteristic 0, where I've just written out what things are modulo p, actually what the graph looks like when you look at p equals 3. And you see it's no longer going to be somehow just a connected graph. It has lots of connected components, and it's only this component that starts up here that corresponds to the irreducible representations of the symmetric group. This is labeling other information over here. And this is something that can be understood combinatorially. Crucially, it comes down again to some multiplicity 1 results that were proved for symmetric groups, and then in their by Kleshchev, and then in their probably the correct generality by Granovsky. And so I want to explain briefly where crystal bases come from. They come from things called quantum groups, which arose in a number of places, including integrable systems. So a quantum group is a deformation of the Lie algebra that depends on some parameter. When you set the parameter equal to 1, you just get back your Lie algebra that you started with. And generically, understanding the representation theory of the quantum group is the same as understanding the Lie algebra. So we have a representation of the Lie algebra we want to understand. We take it to the quantum group, and then we do something crazy. We send t equal to 0. So originally, they're only defined for t being non-zero complex numbers, so you have to come up with the good notion of tending things to 0. And the people in statistical mechanics, I'm told, think of t as being temperature, and that's why we get the name crystal bases. Things start to freeze, and really very important properties persist. The crucial point is that there's also a geometric construction of this crystal basis, this basis as well, which illustrates what a lot of people in algebraic Lie theory are doing now. So this crystal basis arises from something which is from a rather modern part of algebraic Lie theory by taking a limit. So this symmetric group representation theory, from this point of view, is very difficult to understand until you've discovered quantum groups. Okay, so I want to do 1 minute slide on what geometric representation theory is. So if you start with two finite sets, you can look at the space of functions on these finite sets, in values in some field. That just produces two finite dimensional vector spaces. And then if I was to say to look at linear maps between these two finite dimensional spaces, I could write it out in a horrific way to tell you that it just corresponds to multiplication by matrices. Okay? This is me writing this out. The only reason for doing this is you can see that if I try to replace the idea of looking at functions and operators between functions as matrices and look at them this way, I can do all of these operations that are written down here. Summing becomes sum integration. We have pullback. We have push forward. I can do these in lots of different situations where I replace finite sets by things which are much more exotic, algebraic or some nice topological spaces. Functions I then consider, instead of doing just ordinary functions, I might look at cohomology or K-theory, anything that can produce for me vector spaces out of these things and which have these operations of push forward, so that's like integration, and pull back. And then, whenever I look at something which comes from the space on X cross Y, these are called correspondences, I can produce operators on spaces of K-theory or cohomology, and that changes geometry into algebras and representations. And the remarkable thing is that if you look at interesting enough spaces, you get algebras and representations that you wanted to know about, and you can study them geometrically. And in particular, there are sophisticated tools from geometry and topology that allow you to produce representations that you didn't know about before. And this is how one way that quantum groups arise. They arise from things called representations of quivers, and then studying these geometrically, and then doing this convolution construction that was on the previous page. And then you're able to construct something called a canonical base which when t goes to 1, it becomes special bases for Lie algebra representations, and as t goes to 0, it basically produces the crystal basis. And these are the things that are very, very difficult to see in ordinary representation theory, but geometry in characteristic 0 helps you. So the representations of quivers, this is really, in some sense, it was characteristic 0 plays a very crucial role here. Okay, so we can produce this interesting basis via this complicated modern procedure. And then you could ask, well, we've already seen how to try to label at a first approximation irreducible representations and how this Grothendieck group might look like from the crystal basis. We could ask, what does it have to do with the canonical basis? And there's a fundamental problem here. If you study representation theory in characteristic P and try to do some of this difficult geometry is something called intersection cohomology, perverse sheaves, which has as a crucial theorem something called the decomposition theorem, which uses characteristic 0, or things not really being in characteristic P. To get that to work, you have to pass now away from representation theory in characteristic P to characteristic 0, and you do what it this way looks like a cheat. If we start with a symmetric group, it has 2 elements, identity and the involution, and the involution squared is 1. We could perturb this equation to produce this. And now, if I look at this over a field of characteristic 2 and set q equal to 1, then I get this equation back. If I look over the complex numbers and set q equal to -1, then I get a representation of something called the Heck algebra here. But in both cases, in characteristic 2 and in characteristic 0, 1 plus q equals 0. This is a crucial observation, right? And so what you can do is you can replace things in characteristic P with things in characteristic 0 by going from integers to roots of unity. So you can do this for symmetric groups, and there's a very important conjecture which is not understood in much generality, which relates the passage from characteristic P to the passage to the root of unity. The root of unity has everything happening over the complex numbers where geometry and topology are well behaved. And so you find this final theorem that I want to tell you about. If you look at representations of the symmetric group added together, that's encoded in this Grothendieck group, then that's just the same as understanding the representation theory of these Hecke algebras, to such an extent that when you want to look at the simple modules over here, they correspond to canonical basis elements. And when you want to understand more about the simple modules, so how they appear in different types of indecomposable representations, that's encoded exactly in this canonical basis. So this is a rather deep theorem here that involves a lot of this geometric representation theory, encodes enormous amounts of combinatorics, but in principle allows us to calculate whatever we want about simple modules for this Hecke algebra, and hence, if we understood James' conjecture well, about simple modules for characteristic P, Lie algebras. And this is all, on this side, algebraic Lie theory. So that just says what I said there. Unfortunately, we don't know. There's some numerology in James's conjecture, and we don't know how to push that numerology much further. So that theorem that I wrote up here is maybe, I suppose, around 10 years old, something like that. In the last year, that theorem has somehow been souped up into a version that sees not only specializing T to 1 for the quantum group, but keeping the parameter T in there, which is to do with developments from things that are motivated by looking for topological quantum field theories in 4 dimensions. And also, there has been progress in understanding the difficult geometry and topology in positive characteristic. And I particularly want to mention this work of Fiebig. There's a typical result in algebraic geometry that says we understand the representation theory in characteristic P if P is big enough, which are usually wonderful theorems, and the only problem is we don't know typically whether P is bigger than the largest prime that's ever been discovered. So that was the statement of a theorem called the Lustig conjecture. There was lots of very beautiful work that said the Lustig conjecture is true if P is big enough. This work of Fiebig, which is in some sense trying to understand what happens in characteristic P for this type of topological machinery, has now got a bound on P. I don't know exactly. It says P should be bigger than some number. I don't know if we know any prime numbers that are bigger than that yet, but at least it's a number. So I want to end there. That's still the problem. Okay, thank you.
that was a very enlightening talk. I don't know if there are any questions. I think we have time for a few questions. You didn't tell us anything about, this is about sort of the Lie theory aspect of this.
Mm-hmm.
The Lie theory is in Lie algebras as opposed to Lie groups, I think, is what
In the things that I've been presenting today, it's Lie algebras that are appearing, and in particular, this sort of these affine Lie algebras that appear. But there are extremely strong links between representations of Lie groups. So even for the general linear group and the symmetric group here. So the general linear group representation theory, one of the ways to try to understand it is to relate it to symmetric group representation theory by something called Schur-Weil duality, which allows you to try to go between these two procedures. And that's also a very successful way to try to get what you know about Lie groups and how they act on interesting spaces and push it across to the symmetric group. It's a very productive way to try to understand that too. But I didn't mention any of that today, I'm sorry.